Imagine downloading like the most visually complex, spatially demanding puzzle game on your phone.
Okay, I'm picturing it.
Right. So we are talking about a game that requires you to like physically spin your device in these perfect 360-degree circles.
Oh, wow.
Yeah, perfectly parallel to the ground,
Yeah.
trying to match up these really intricate glowing graphics on the screen.
It's pretty intense.
It is. But now imagine beating that exact same puzzle with your eyes completely closed.
Wait, really?
Yeah. Or better yet, imagine you are completely blind and you are navigating that intensely visual spatial puzzle just as flawlessly as someone with perfect 20/20 vision.
I mean, that sounds like a magic trick. Or at least it sounds like they made a totally different, watered down version of the game for accessibility.
That is exactly what you would assume,
Yeah.
but it isn't. It is the exact same code, the exact same puzzle, just rendered in a completely different sensory language.
That is fascinating.
Yeah, right. And that is exactly what we are unpacking today. Welcome to the deep dive. If you're a learner who's constantly trying to understand the hidden mechanics of the world, if you want the signal without drowning in all the noise, you are in the right place.
Glad to be here for this one.
Today we are looking at how Apple's software engineers, alongside some incredibly creative indie developers out there, are making the impossible happen on the devices sitting in our pockets right now.
Yeah, and we are pulling our insights today from a really brilliant session out of WWDC 25, which is Apple's big developer conference.
The presentation is called Principles of Inclusive App Design.
Exactly, led by two of their accessibility designers, Chris and Lisa. But just to be super clear right up front, we aren't just here to read like a technical coding manual to you.
No, definitely not. We are here to fundamentally rethink what the word disability actually means.
Right.
We're going to deconstruct how the digital world is built and explore this really counterintuitive idea. The idea that designing your technology for the absolute extreme margins of human capability actually makes that technology infinitely better, more creative, and more resilient for absolutely everyone else.
Including you, listening to this right now.
Exactly. So to get to that crazy puzzle game I mentioned, we really have to start with a foundational reality check.
Yeah, Chris and Lisa hit the audience right out of the gate with this statistic that it completely reframes the entire conversation.
It really does. Globally, about 1 in 7 people has a disability.
1 in 7. I mean, just let that sink in for a second.
Okay, let's unpack this.
Yeah.
Because 1 in 7, let's really visualize that.
Sure.
Think about your extended family or, the people in your office. Think about the lineup at your local coffee shop this morning.
Right, if you just put 7 people in a room.
Statistically, one of them navigates the world with a disability.
Which completely takes this concept of accessibility out of the realm of like niche, marginalized charity work.
Oh, 100%.
It places it squarely in the dead center of the typical human experience.
Which means even if you, the person listening to this, do not personally identify as having a disability right now, the mathematical probability is incredibly high that someone you love or someone you manage at work does.
Or even your future self.
Exactly. It's basically an inevitability of biology.
And when Apple's designers approach this, they don't just look at disability as this massive monolithic block,
Right, because that's not helpful for engineering a solution.
Exactly. They break it down into 5 distinct categories so developers can actually start solving for it. And those are vision, hearing, motor, speech, and cognitive.
Vision, hearing, motor, speech, and cognitive. Basically how we take information in, how we process it, and how we interact with the world around us.
Yeah, that's a great way to summarize it.
But here is where society, and frankly a lot of software developers too, get it fundamentally wrong.
We love a binary.
We really do. We love a light switch. You're either totally blind or you have perfect vision. You are either entirely deaf or you have superhuman hearing.
It's the all-or-nothing fallacy. But human biology almost never operates like a light switch.
No, it operates on a dial.
Right. And the presentation uses this brilliant lived example from Lisa herself to just completely shatter this binary assumption.
Yeah, so Lisa is legally blind. She has a form of macular degeneration.
And when most people hear the phrase legally blind, they just imagine, like, a world of total darkness.
Right, they imagine a complete void, but that isn't her reality at all.
No. Macular degeneration mainly impacts central vision and the ability to process fine detail.
So for her, her vision is incredibly blurry. She mentioned she has to get extremely close to a screen to read a text message or right up to a person's face to recognize who they are.
Right, but this is the crucial part. She can still see colors. She can still see ambient light. She can track large objects moving in her peripheral vision.
She isn't existing in a void. She's existing on a spectrum. She has some vision.
And Chris and Lisa emphasize that inserting that single word, the word some, is one of the most powerful paradigm shifts a designer can possibly make.
Because it forces you to stop designing for a light switch and start designing for a dial.
Exactly.
Let's unpack the mechanics of that dial for a second. If I am a developer and I'm designing for a light switch, I assume my user either needs the standard, flashy visual interface, or they need a totally blank screen that just reads text aloud like a robot.
Right. There's absolutely no middle ground in that scenario.
None. But if I design for a dial, I suddenly realize that a user might need the text to be scaled up, like 300%, while still relying heavily on the color-coded buttons to navigate.
Because they have some vision.
Exactly. Acknowledging some vision or some motor control opens up this massive universe of necessary engineering choices.
Which actually brings up a fascinating philosophical question.
What's that?
Well, why do we default to the light switch in the first place? Like, why does our physical and digital architecture assume these rigid binaries?
Oh, right. They talked about this. It comes down to this subconscious bias we have about human development.
Yeah, the myth of the flawed human arc.
This was such an interesting part of the text. Society has this baked-in, almost fairy tale narrative of how a human life is supposed to progress.
We assume we are all born completely incapable.
Yeah.
Can't walk, can't talk.
Right, and then we steadily learn those things, hitting all these perfect little milestones.
And then we supposedly plateau as these fully capable, independent adults with perfect sensory and motor functions.
Until the very end, where we predictably and uniformly lose those abilities in old age.
It's treated like a perfect mathematical bell curve that just applies to every single human on Earth.
And because society implicitly believes this arc is universal, we build our entire infrastructure around it.
Right. Our schools, our transit systems, our software, they cater exclusively to the people sitting right at the very peak of that bell curve.
But, okay, let me push back on this for a second, just to play devil's advocate.
Let's go for it.
Even if the bell curve is a generalization, biology is real, right? I mean, if someone is born totally blind, or if they are paralyzed in a car accident, that is a biological limitation.
Sure.
So how is that a flaw in society's assumption? A broken leg is a broken leg.
That is a really crucial distinction to make. What's fascinating here is how we define the terms. The medical condition, so the broken leg, the macular degeneration, that is an absolute biological reality.
Right.
But the disability, the inability to participate in the world is something entirely different.
Okay, see where you're going.
The core argument here is that disability is not simply a characteristic of a person's body or mind. It is actually born from the environment.
It emerges specifically in the gap between what a person's body can do and what the environment expects them to do.
Exactly. It's the inclusion gap.
Walk me through the mechanics of that.
Let's use an architectural analogy from the source. Imagine a two-story building.
Okay.
You have a person who uses a wheelchair, and they have a really crucial meeting on the second floor.
Yeah.
If that building only has stairs, that person is facing a severe, limiting disability. They cannot get to the meeting.
Right, the environment is blocking them.
Now, retrofit that exact same building with an elevator. The person's biology hasn't changed a single bit.
Their wheelchair hasn't changed.
Nothing about them changed. But suddenly, their limitation entirely vanishes. They get to the meeting just as easily as anyone else.
They are no longer disabled in that specific context.
Because the environment adapted to their physical reality. The disability existed entirely in the gap between the stairs and the wheelchair.
And we can actually flip that analogy to prove how universal it is, too.
How so?
Imagine that same building. Stairs only, no elevator. Now imagine a person who has full, perfect use of their legs. They're right at the peak of that mythological human bell curve.
Right.
They show up for their meeting, but there's a chain across the staircase and a sign that says, "Stairs under construction, do not use."
Yeah. Suddenly, the person with full use of their legs is completely disabled by the environment.
Exactly. Their biological capability is completely irrelevant because the environment does not afford them a way to use it.
It proves that disability is a dynamic, fluid state created by a mismatch between the human and the world around them.
And historically, whenever humanity has been confronted with this mismatch, it has actually been the single greatest driver of our innovation.
The historical context they brought up is just fascinating here. Think about the microphone.
Oh, right.
It wasn't just invented as some fun novelty. It was engineered because the human voice, biologically, is not naturally loud enough to meet society's expectation of addressing crowds of thousands of people.
The gap between our biological volume and the environmental expectation basically birthed modern audio engineering.
Same thing with glasses. We don't view wearing glasses as a profound disability today, but why were lenses invented in the first place?
Because blurry vision clashed heavily with society's relatively new expectation that humans should be able to read small text and printed books.
The environment demanded a biological capability that millions of people simply didn't possess. So we invented a bridge. We closed the gap.
But the most tangible, universal example of closing the gap, and the one that directly maps to software development, is the curb cut.
The little ramps that dip down from the sidewalk to the street level at crosswalks?
Exactly. For decades, sidewalks were built with these sharp, 6-inch concrete drops down to the street.
Society just assumed everyone navigating a city was walking on two fully capable legs.
But for a person in a wheelchair, that 6-inch step was an environmental brick wall. It was a massive inclusion gap.
And those didn't just appear out of nowhere, because city planners were feeling particularly generous one day. There's real deep history there.
Deep history. In the 1970s, disability rights activists, led by figures like Ed Roberts at UC Berkeley, literally had to go out in the middle of the night and pour their own crude cement ramps against the curbs.
Just so they could cross the street independently.
Yeah, they forced the issue. They fought for the implementation of curb cuts. And eventually, the law required the concrete to be smoothed into a ramp to accommodate wheels.
Now let's connect this directly to you, the listener.
Yeah.
Think about your own daily routine. When was the last time you were incredibly grateful for a curb cut?
Oh, constantly.
Have you ever pushed a baby stroller through a neighborhood? Have you ever ridden a bicycle and smoothly transitioned onto a sidewalk without having to dismount?
Or what about dragging a 50-pound rolling suitcase from a hotel lobby to a taxi?
In every single one of those scenarios, you were benefiting from a structural design choice that was initially fought for by and designed for a marginalized group.
You, with your heavy suitcase, had a temporary situational limitation. The environment was suddenly at odds with your goal.
But because the architecture had already been fundamentally altered to accommodate a wheelchair, it's seamlessly accommodated your luggage.
That is the ultimate magic trick of inclusive design. It inevitably trickles down.
When you design for the margins, when you fix the environment for the people who face the absolute most friction, you accidentally make the world smoother and more efficient for the masses.
So if this inclusion gap is essentially a mismatch between what engineers assume people can do and what people can actually do, how do developers stop making bad assumptions?
That's the million-dollar question.
Like, if I'm writing an app, how do I know where the digital curbs are before I even compile the code?
Well, you'd probably assume empathy is the best starting point, right?
Yeah, I'd assume an able-bodied developer can just close their eyes, navigate their app to see what it feels like to be blind, and then design a solution based on that feeling.
You'd think so. But the tech industry is learning the hard way that this approach is deeply, deeply flawed.
Really?
Yeah. Empathy is a noble starting point, sure, but relying solely on able-bodied engineers to simulate a disability and guess what a user needs almost always leads to frustrating broken software.
Because you can't actually simulate it.
You simply cannot simulate a lived experience.
Which brings us to a phrase that is basically the golden rule of this entire space. The disability rights activists who fought for those curb cuts had a central mantra: nothing about us without us.
Nothing about us without us. It means no policy, and by extension, no technology, should be created without the full, active participation of the people it will actually impact.
If an able-bodied developer tries to guess what a blind user wants, they might assume, oh, they can't see, so they must want a deeply simplified interface with way less information so they don't get confused.
Right, but if they actually brought a blind user into the room, they might learn the exact opposite.
Like what?
Like, because I can't visually scan the screen, I actually need more detailed, highly structured audio descriptions to understand the context of what I'm doing.
You only learn that by asking. The lived experience is technically superior to the most well-intentioned guess.
And while tech giants and indie developers are increasingly collaborating directly with the disability community, they still need a concrete framework to build on.
How do you actually start building a digital curb cut?
Well, Chris and Lisa lay out 4 very practical, highly technical steps. And the first one fundamentally challenges how we output data.
Okay, let's get into the mechanics. What's step 1?
The first principle is designing for multiple senses, or sensory redundancy. You have to provide information and allow for input in multiple redundant ways.
Give me an example of what not to do.
If your software only communicates a critical error state by turning a text box red, you have instantly excluded anyone who is completely blind and anyone who has red-green color blindness.
Because the data is locked behind a single sensory gate.
Exactly.
The classic example of fixing this one we've all benefited from is video captions.
Oh, absolutely.
They were originally championed strictly for the deaf and hard of hearing community. But again, the trickle-down effect is massive.
You're watching a video on a noisy subway train without headphones.
Or you're scrolling a social feed in a really quiet library.
Captions allow you to consume what is inherently auditory data using your visual sense. The app adapts to your situational environmental limitation.
Apple is taking this concept of sensory redundancy much, much deeper with a feature highlighted in the session called Accessibility Reader.
Here's where it gets really interesting. Accessibility Reader allows you to customize the reading experience of a web page or a document. Naturally, it provides visual text, but it also offers a purely auditory experience.
You can just hit play, drop the phone in your pocket, and listen to an article.
Right. That caters to the visually impaired or just the person walking down a crowded sidewalk who can't safely look at a screen. But the real breakthrough is in the synchronization.
Yeah, as the accessibility reader speaks the words aloud, it simultaneously highlights that exact word on the screen.
It pairs audio output with a highly precise visual tracking mechanism.
But wait, let me play devil's advocate again here.
Okay.
If I have a cognitive processing issue, say severe ADHD, or I'm recovering from a concussion, isn't blasting me with audio and moving visual text at the exact same time going to cause massive sensory overload, it sounds like it could make it worse.
That is a fantastic point, and it's exactly why just slapping extra senses onto an interface isn't enough on its own. However, in the case of reading, for many people with dyslexia or attention deficits, processing a massive block of static visual text is exhausting.
The eyes jump around, they lose their place.
Right. By providing dual sensory input, seeing the word highlighted at the exact millisecond you hear it spoken, the device basically acts like a metronome for your brain.
It anchors your focus.
Yes. It drastically reduces the cognitive load required to track the information.
It's literally holding your hand through the data. And third-party developers are building incredible tools using this multiple sense philosophy too. There is a recipe app they highlighted called Crouton.
Crouton is a digital cookbook. Now think about the traditional mechanical action of adding a recipe to an app. You have to type it out with your thumbs.
Which requires intense fine motor control and sharp visual focus on a tiny digital keyboard.
Right. But Crouton offers a buffet of sensory input options. You can type it, sure, but what if you have a motor tremor and cannot tap those tiny keys?
Crouton lets you import a recipe using the camera.
Exactly. You point the lens at a physical cookbook, the app uses optical character recognition, and it extracts the text automatically.
You bypass a motor requirement by substituting a visual tool.
But the feature that perfectly illustrates permanent versus situational limitations is their hands-free mode.
Oh, this is so good. So you are looking at a recipe, you activate hands-free, and the app will walk you through the steps without you ever physically touching the glass.
You navigate entirely with your voice, or by using the camera to track your facial gestures.
Obviously, this was engineered for users with severe motor disabilities.
If you don't have the use of your arms, a hands-free UI is the difference between cooking a meal independently or not cooking at all.
But bring it back to your own kitchen on a Tuesday night. Ask yourself, listener, have you ever been making meatballs? You have your hands deep in raw egg, breadcrumbs, and ground beef.
And you suddenly need to know how much garlic to add.
You absolutely cannot touch your pristine smartphone screen without turning it into a salmonella biohazard.
Right? In that exact moment, your physical activity has created a severe environmental limitation. You have a temporary motor disability.
But because Crouton was built with a digital curb cut for permanent motor disabilities, you just use the hands-free mode.
You nod your head, the recipe advances to the next step, and your screen stays perfectly clean.
The inclusive design choice instantly became the ultimate convenience feature for the able-bodied user.
Now, your earlier pushback about sensory overload was spot on. Providing multiple sensory inputs, sight, sound, voice control, is amazing. But what if the specific visual option the developer provides is still too loud? Or what if the audio speaks too quickly?
This is where we move past just offering options and get into step two, which is the absolute necessity of deep customization.
The software has to be able to physically reshape itself to fit the user's brain.
Precisely. We are talking about deep structural customization. The philosophy here is that the human should never have to adapt to the app.
If we connect this to the bigger picture, the app must dynamically adapt to the human.
We mentioned Accessibility Reader earlier. It doesn't just read to you, it makes you the art director of your own screen.
You can adjust the text size, you can invert the contrast, you can change the font entirely.
They specifically highlight allowing users to select high legibility characters within Apple's San Francisco font.
Let's explain the mechanics of that because it's tied to something called dynamic type.
Okay, yeah.
In the old days of app development, a coder would hard-code a text box to be exactly, say, 14 pixels high. If you needed it bigger, too bad.
The box won't budge.
But with dynamic type, the developer builds a flexible container. If a low-vision user tells their iPhone, I need all text globally scaled up 300%, the OS tells the app to expand.
And because it's dynamic, it doesn't just magnify the text so it bleeds off the edge of the screen and becomes unreadable.
No, it reflows the margins, it moves buttons around to make room, it fundamentally alters the UI layout on the fly to accommodate the massive text.
And when they talk about high legibility characters, they mean literally altering the shape of the letters.
Right. For someone with low vision, a lowercase I, an uppercase I, and the number 1 can look like an identical vertical line.
High legibility mode alters the geometry of the font to make those characters distinct.
But the most striking example of customization for cognitive accessibility comes from a third-party app called Carrot Weather.
Oh, carrot weather. Weather data is inherently chaotic.
It really is. It's percentages,
Yeah.
radar gradients, wind vectors, pressure graphs.
Carrot weather handles this by catering to two totally opposite ends of the cognitive spectrum. The presentation shows their default interface, which is incredibly dense.
It is a data-rich matrix designed for hardcore weather nerds who want every single data point packed onto one screen.
But for a user who is neurodivergent, someone who is easily overwhelmed by visual noise, that dense screen is physically stressful to look at.
It's too much competing information. It creates a massive cognitive inclusion gap.
So, Carrot Weather allows you to ruthlessly strip away the interface. With a few taps, you can hide the radar, kill the wind vectors, delete the humidity percentages, and reduce the entire app to absolute minimalism.
Just the current temperature and an icon of a cloud.
And we really need to emphasize this. For someone easily overwhelmed, removing clutter isn't an aesthetic preference.
No, it isn't about minimalist design trends. It is a strict functional accessibility requirement.
By letting the user dial the data density up or down, the app becomes a bespoke, custom-fit tool for every individual brain that opens it.
Okay, I am tracking with all of this. But if I am an indie developer making an app in my basement, I'm probably panicking right now.
Right. You're telling me I need to build a dense data matrix, a minimalist interface, a facial recognition voice control system, an optical character scanner, and a dynamic text reflow engine, all from scratch.
I don't have the budget or the engineering power of Apple. That sounds completely insurmountable.
And if they had to build all of that from scratch, the digital world would remain entirely inaccessible. The barrier to entry would be financially impossible.
But they don't have to build the tools, they just have to plug into them. This is step 3, unlocking potential with accessibility APIs.
API, Application Programming Interface. Let's look under the hood. What exactly is an API doing in this context?
Think of an API as a pre-built, standardized translator. The iPhone operating system has these incredibly powerful assistive technologies built deeply into its core, things like voiceover, switch control, voice control.
Or the larger text scaling we just talked about.
Exactly. On the other side, you have the indie developer's app. The API is the standardized bridge that connects the app to the device's built-in tools. Adopting them is the digital equivalent of pouring the concrete for a curb cut.
You don't have to invent the wheelchair, you just have to make sure your digital sidewalk connects to it.
Precisely. When a developer builds a standard button in Apple's coding language, Swift UI, the system automatically tags it for the accessibility tray.
Wait, what is the accessibility tree? That sounds crucial.
It is the absolute backbone of digital inclusion. When you look at an app, you see a visual interface, colors, shapes, pictures. But the operating system maintains a hidden, invisible database running in the background called the accessibility tree.
It's a purely structural map of everything on the screen.
It tells the OS, there is an element here, it is a button, its function is submit, its state is unclicked.
So assistive technologies don't actually look at the visual screen, they read the hidden tree.
Let's look at an API like switch control. This is designed for users with severe motor limitations who cannot touch the glass screen at all and maybe cannot speak clearly enough for voice commands.
How do they navigate?
They navigate the phone using physical hardware paired to the phone, Bluetooth buttons, sip and puff straws, head arrays.
So how does puffing on a straw let you navigate a complex touchscreen app?
Through the API and the accessibility tree. When switch control is active, a highly visible colored square outline appears on the screen. The operating system looks at the accessibility tree to see where all the interactive elements are.
Oh, I see.
The user clicks their physical switch once, and the square jumps from the back button to the settings button. It systematically scans the UI.
And when the square highlights the button they want, they click their second switch, and the OS registers a tap on the glass.
And this is the massive trap for developers. If an indie developer builds a custom, fancy-looking button from scratch, but fails to use the API to label it in the accessibility tree, the system doesn't know it exists.
The scanning square will just jump right over it.
The user is entirely trapped. The bridge is out.
Which brings us to the most powerful API of them all, and the promise we made at the very beginning of this conversation. We have to talk about VoiceOver, and we have to talk about Black Box.
VoiceOver is Apple's built-in screen reader. It allows a user who is completely blind to navigate their device entirely through spoken audio.
You swipe your finger around the blank glass, and the phone speaks aloud whatever UI element is sitting under your finger.
By reading that accessibility tree we just talked about.
It's an incredible piece of engineering, but Chris and Lisa highlight a third-party app that uses the VoiceOver API in a way that is so wildly creative, it just redefines what is possible. The app is a game called Black Box.
Black Box is infamous.
Yeah.
It is a notoriously difficult, highly abstract puzzle game that forces you to interact with your phone in bizarre ways. You almost never solve a puzzle by just tapping the screen.
Right. You might have to solve a puzzle by plugging your phone into a charger, or waiting for a full moon, or screaming into the microphone. It relies on the iPhone's internal hardware sensors, and it is a deeply, intensely visual game.
The session highlights one specific puzzle that relies on the gyroscope, the internal sensor, that knows exactly how the phone is oriented in physical 3D space.
So picture this puzzle if you are an able-bodied, sighted player. The game requires you to hold your phone completely flat, parallel to the floor, and then you have to slowly, physically rotate your body in the phone a full 360 degrees in a circle, like a compass needle.
Visually on the screen, there are intricate glowing dashes that light up in a circle as you hit the exact right angles. It's a spatial visual puzzle.
Now stop and think about the mechanics of that. How on earth does a player who is completely blind play a visual spatial gyroscope puzzle?
If you just turn on a standard screen reader, the accessibility tree might just read graphic, unlabeled button, background image.
That provides zero actionable data to solve a puzzle.
But the developer of Black Box didn't accept that inclusion gap. They fully embraced the VoiceOver API and essentially built a secondary, invisible version of the game that runs purely on audio and haptics.
They didn't just label the buttons, they used semantic UI to label the mechanics of the puzzle.
When a blind player opens this exact gyroscope level, VoiceOver doesn't just read the title of the game. It intercepts the user's swipe and speaks a highly customized, specific clue. 360 dashes in a circle.
360 dashes in a circle. In an instant, the blind player is handed the exact same conceptual puzzle framing that the visual player gets from looking at the graphics.
But the real magic is in the execution of the gameplay.
As the blind player holds the phone flat and begins to physically turn their body, the game harnesses the API to output rich, spatial audio design and haptic feedback.
Haptics are those highly precise, sharp little vibrations generated by the phone's internal motor.
Right, it's not just a generic buzz, it feels like a physical click inside the glass.
So as the blind player rotates, the game maps the visual data array to an auditory and tactile array. When they sweep past the correct angle, the audio cue pitches up dynamically, and the phone delivers a sharp haptic tap to their hand.
They are literally feeling the visual graphics.
They are navigating a digital 3D space purely through sound frequency and microvibrations. A completely visually reliant spatial puzzle has been perfectly, flawlessly translated into a sensory language that a blind player can fully master independently.
They aren't playing a dumbed-down accessibility mode. They are playing the exact same intensely difficult puzzle, utilizing the exact same gyroscope data, just rendered through a different physical sense.
It is a profound engineering achievement. It proves that there is virtually no concept, no matter how visually complex or spatially demanding, that cannot be translated if a developer is willing to be creative, map their data correctly, and utilize the APIs available to them.
It honestly gives me chills. But hearing all this, seeing this level of absolute perfection in an app like Blackbox, it makes me wonder, is the job ever done?
What do you mean?
Like, if I'm a developer, do I ever reach a point where I compile my code, ship it to the App Store, and say, behold, the perfectly inclusive app featuring zero barriers for any human being on Earth?
That is the exact trap developers fall into. The idea of perfect inclusion is a complete myth.
So what does this all mean?
The source material addresses this with refreshing honesty by introducing step 4, acknowledging inclusion debt.
Let's relate this to a concept software engineers are very familiar with: tech debt. When you are building software, sometimes you take a shortcut in your code to get the product shipped on a deadline.
You know the code is messy, you know it's inefficient, but it works for now.
You are borrowing time today, fully knowing you will have to pay it back with interest later when you go back to refactor and clean up that code. That's tech debt.
Chris and Lisa introduced the parallel concept of inclusion debt. It is the profound, necessary realization that inclusion is a continuous journey, not a final destination.
It is not a QA checklist you just check off before launch.
Because human diversity is simply too vast.
Exactly. You will inevitably release an app that has an inclusion gap. You will miss a nuanced use case. You will inadvertently build a digital staircase and forget the elevator.
The danger is not that you possess inclusion debt. The danger is ignoring it or pretending your app is somehow finished.
This raises an important question. How do the best developers handle knowing their app is fundamentally flawed for someone out there?
By actively, relentlessly tracking the debt, by seeking out the friction points. And the presenters don't just point fingers at indie developers, they point the mirror directly at Apple itself, which I found incredibly compelling.
Yes, they use their own brand new flagship feature, the accessibility reader we were just praising for its dual sensory input, as their primary example of inclusion debt.
They stand up on stage and openly admit that even this incredibly advanced, highly engineered tool has known room to grow.
They note that the current iteration needs better text formatting for enhanced readability, and it needs more options to support different cognitive reading styles.
They are publicly acknowledging the gap in their own work.
But because they acknowledge it, because they have actively written it down on the ledger as inclusion debt, they can consciously plan for it in their next engineering sprint.
They know exactly what architecture they need to build next. The gap is no longer viewed as a failure. It becomes the explicit roadmap for their next wave of innovation.
And that perfectly encapsulates the cyclical beauty of this entire process. You find an inclusion gap. You collaborate with the disability community to deeply understand the lived experience of that gap.
You invent a technical solution.
That solution inadvertently spawns new ideas for the able-bodied community, which in turn reveals new, deeper gaps, and the cycle continues, constantly pushing the technology forward.
It is a continuous evolution toward a more malleable world.
All right, as we pull back and synthesize this deep dive, let's recap the fundamental shift in perspective we've explored today.
The core philosophy you must walk away with is this. Disability is not a static medical condition isolated entirely within a person's biology. It is a dynamic, contextual state that relies heavily, almost entirely, on the environment.
And in the digital age, software developers and UI designers are the literal architects of that environment. They hold the power, through their code, to either construct impassable barriers or pour digital curb cuts.
By embracing the absolute necessity of the mantra, nothing about us without us, and utilizing the frameworks discussed engineering sensory redundancy, building deep structural customization through dynamic type, adopting accessibility APIs so the hidden accessibility tree is robust, and honestly tracking inclusion debt developers can systematically close those gaps.
And for any software engineers listening who want to move from theory to implementation, the WWDC session explicitly recommends 2 immediate next steps. First, go back and watch the technical deep dive from WWDC 24 titled Catch Up on Accessibility in Swift UI.
That will show you the actual syntax of building that accessibility tree.
Second, review the WWDC 25 session. Evaluate your app for accessibility nutrition labels.
The nutrition labels are vital because it's how you highlight your app's accessibility features right on the App Store front page, so users who rely on those specific tools can actually find your work before they download it.
It's about making the invisible architecture visible. Now, before we sign off, I want to leave you, the learner, with a thought to chew on. Something that builds purely on the implications of everything we've discussed today, but takes it one step further out into the future.
I love a good thought experiment.
We've spent this entire hour talking about the digital world. We've seen how software like the Accessibility Reader or Carrot Weather or Crouton can instantly, dynamically reshape their colors, their layouts, their text sizes, and their sensory outputs to perfectly fit the unique physical and cognitive needs of the user holding in the device.
The software is infinitely, instantly malleable.
But what about the physical world?
Oh, wow.
If our digital environments are becoming this perfectly adaptable, if our phones can instantly reconstruct themselves to suit our biology in real time, how long until we demand that exact same level of fluid customization from our physical architecture?
That is a staggering implication.
Will the homes we live in, the office buildings we work in, and the transit systems we navigate eventually have to become as dynamically adaptable as the software on our screens? Imagine walking into a room and the physical walls, the ambient lighting, and the acoustic dampening instantly adjust themselves to respond to your specific sensory processing needs.
Communicating seamlessly with your device, just like an API.
Exactly. If the environment creates the disability and we are finally learning how to instantly rewrite the digital environment to erase that disability, how long until we expect to instantly rewrite the physical one?
It suggests an inevitable future where the physical world bends entirely to the human, rather than forcing the human to bend to the world.
It really does. Thank you for joining us on this deep dive. Keep looking for those inclusion gaps in your own daily life, whether you are swiping on a screen or walking down the street. You might just find the inspiration for the next great human innovation hiding right inside them. Until next time.